Okay, students, hello. This is, I believe, our final chapter for this particular course. This is chapter 9, and it's titled Image Quality and Characteristics. There's a lot of information in this chapter, and I'm going to try my best to talk slowly, but also to stay within a decent time limit so you don't have to waste your time listening to this. Some of this you could probably, skip through, but I want to cover a whole lot more than what's listed on Blackboard for you. As usual, here are the objectives that I got from the text itself, and the majority of these we will cover. We're going to talk about the components of radiographic image quality, and then talk about visibility and sharpness of a radiograph, and then we're going to talk about the importance of brightness or density and contrast. Then we're going to differentiate between tissues with a high and low subject contrast. Talk about the importance of spatial resolution or recorded detail. So this and this up here that says or, what we'll find out is that one of these words is associated with digital terminology and the other is film. So we will not be talking about film, but I will just mention it when we come to those parts. Then we're going to talk about size and shape distortion, but very briefly because you've covered that before. And then recognizing the effect of quantum noise and scatter when it comes to digital image. We're also going to talk about the effect of image artifacts and then the actual digital image characteristics of matrix and pixels. If you've never had any type of computer course and you don't understand what these are, I can refer you to a little bit more information, but this is assuming that you already know some of these computer terms. Then we're going to compare the dynamic range between film screen and digital. Again, film screen is not on your exam and it will not be on your final registry, but sometimes knowing the difference gives you an idea of where we've come over the years. And then we're going to talk about bit depth, its effect on quality, and then the specific digital characteristics of brightness, contrast, and resolution, and then we'll compare it to film screen. And then we're going to talk about how we adjust the window level and window width and what those are. Then we're also going to talk about high and low contrast radiographic images. Now, these right here, that was good grammar, wasn't it? These objectives describe sensitometry and sensitometric curves. All of these are actually associated with film. So I listed them because they're listed in your textbook, but you will not be responsible for any of this. And you will notice that we don't even actually look at them later on. So they're here, but you can just ignore them. Now, condensed, these are the three objectives that are listed in your course syllabi or on your Blackboard under this module, and it's classifying the aspects of a radiographic image that are affected by changes in technical factors. So we've already talked about the exposure factors that we have to have knowledge of, how to use them, how to adjust them, and we've also talked about secondary factors, and then we've talked about accessory devices or collimation and grids and things like that. But this is putting them all together and knowing how each one of those changes will affect your image. So this is pretty much bringing it all in together into one big, this is how we take a quality image. We're also going to talk about terminology that is used with digital imaging, and these are terms that you need to know. You will discuss them more in another course next quarter called Radiographic Equipment and Acquisition, but this is a nice introduction to it. And then we're going to talk about image characteristics when it comes to the digital world, okay? So let's get started. What is a radiograph? What makes a good image? I know a lot of you may have heard maybe getting your own x-ray or just shadowing whatever experience that you may have. A lot of times we use the word picture, and it's a little deceiving because people then assume that it's just a camera without the ionizing radiation. So we need to understand when it comes to a radiograph, we are using ionizing radiation to interact with the body to then go through to our image receptor and make a latent image. After that latent image is processed, whether it be filmed through a chemical processor or a digital image through computer processing, either one of those will affect the quality image that you are shooting for. So it's really important to know what is a radiograph and what it actually consists of. Now, if you take a look at this right here, that's more like a picture, but it's also a radiograph. This is a real ceramic pig that was x-rayed with some coins in there so that you can see what it looks like on the inside. So the terms that you'll hear me talk about in this particular chapter, like if differential absorption produces the image, then that image should be representative of the anatomical part. Is that true? Yes. Everything that you x-ray, you have to use the appropriate technical factors to ensure that if you're taking an image of a leg, then you want the bone, the skin, the muscle, and if there's possibly a foreign object. So you have to make sure that all of those are affected by the exposure factors you choose in the beginning. What factors actually affect that quality image? That's what we're going to look at, and then we're going to learn some new terms that we use in the digital system of imaging. So let's get started. So when it comes to a quality radiograph image accurately represents the anatomic area of interest, and information is well visualized for diagnosis. It is important to identify the characteristics of a quality radiographic image before you can comprehend the factors that affect its quality. That means all of the things that we've already talked about, mass, KVP, adjusting your time, even the inverse square law, the direct square law, reciprocity, all of those things come into taking that radiograph. Now we're talking about the quality of that radiograph and how we put them together. Radiographic images can be acquired two different types of receptors. It can be a digital or a film screen, and the process of creating that latent image by differential absorption is the same for both of them. It is the acquisition, the processing, and the display that actually vary. And with those variations, that's what we want to talk about. This chapter focuses on the characteristics of a quality image that is displayed on a computer monitor. That is what you will work with when you go into the clinical arena. We're going to first talk about the visibility and sharpness factors that comprise a quality radiographic image, and we may discuss digital and film screen at times. And then some characteristics may be compared to film, but there are no film components on the test or on your registry. And I'm going to continue to say that, but you should never say, well, I don't need to know about film. Well, you need to know how digital has improved, okay? How it has improved not only our job as a radiologic technologist, but how we get much better quality images now that we have digital. Following our discussion on image quality, digital and film screen imaging, we'll discuss those separately to distinguish their characteristics. And then we'll talk about the construction of image receptors and how it's acquired, processed, and displayed in the rest of the textbook in your next course. So this is just an introduction so that you understand some of these terms, okay? So here we go. So when it comes to images in radiology, an image is made up of photographic qualities as well as geometric qualities. When we think of a radiographic image, one of the first things, and I say this a lot, maybe the Southern in me, who knows, but is it pretty enough? Or pretty? So if it's pretty, now this is an actual x-ray of a flower, so that's kind of impressive to look at. But what we want to see when we take our images are the anatomical structures. Can we define where each structure actually starts and then ends? Can we see the outline of each area that we have radiographed? Is the part that we're looking at visible? Is it too dark or too light to be of diagnostic quality? Those are some of the questions that we look at when we define photographic properties of an image. And that's all about being a pretty picture. Now even this flower, this is the stem. See how much darker it is on our x-ray? Because it's made of something different from the bloom or the petal of the flower itself. And if you go back to, I don't know, middle school biology, where we talked about the stamen and the, I can't even think of all the words that come with the plant, but each one of those can be seen individually. Even in this petal, we can see where the middle one is a little darker than the rest of it. So it's just, that is a photographic property. When we take an x-ray of a human body, say it's an abdomen, we still want to be able to see everything separately. We should be able to see the bone and the spine and the pelvis, plus the air in the colon or in the intestines, or maybe contents in the bowel. You know, that's all very important. But when we look at the geometric properties, which is what we've kind of already talked about before, we want to know if the product or the part that we have just x-rayed is true to life. Is it exactly what we expected? Or is it distorted? And if it's distorted, what caused that distortion? Can we see bony detail if we're looking at the bones? And is it sharp enough that is what we call diagnostic quality? So photographic properties here, structures being separate, dark or light, and then geometric properties, true to life, bony detail, and sharpness. This is an older graph that we divided into photographic versus geometric properties, and it wasn't too hard to find this because it's just a few editions ago, but this is the way it actually used to be listed. And when it comes to photographic properties, we are talking about visibility, and that's density and contrast. Then it comes to geometric properties, it's sharpness, recorded detail, and distortion. Well, this is what image quality is in your textbook, and this is the way we look at it today. The visibility of the anatomic structures and the accuracy of their structural lines recorded, which is their sharpness, determines the overall quality of the radiographic image. Visibility of the recorded detail refers to the brightness or the density and the contrast, and you'll understand in a little bit why I keep saying brightness or density, but this is separate from contrast on the image. Visibility of the anatomic tissues is achieved by the proper balance of image brightness or density and contrast, and that's what we refer to as photographic. Then when we talk about the accuracy of the structural lines, which is sharpness, is achieved by maximizing the amount of spatial resolution or recorded detail, could be here, and distortion, and minimizing the amount of that distortion. These are the geometric properties. This actual image showing these two side by side is in your text. It's figure 9.1, so if you want to go back and look at that. So remember, we no longer call them photographic and geometric. We talk about the visibility, which is photographic, and then the sharpness, which is geometric properties of a radiograph. And that's changing from the old school of film to digital that we have now. So now let's go to photographic properties. A radiograph that has optimal radiographic brightness, contrast, and spatial resolution are digital properties of a very good photographic property of an X-ray. Now, this is an X-ray of a shell, and right here, why is this nice and it's bright enough that we can see the denser part of the shell. This does not have as much shell in it, so there's air here, so that's the contrast between the two. And then when it comes to spatial resolution, we can see the actual lines of that shell, and I just think these are fascinating. But when it comes to what we do every day, it's talking about brightness or density. So let's take each one of those individually. So go back here, brightness, contrast, spatial resolution. Let's start with brightness. Now, brightness or density. How the radiograph is displayed determines whether to evaluate the image in terms of brightness or density. Digital images are typically displayed on a computer monitor, and film screen images are displayed on film. Digital images can be printed on film, but it's not the same type of film. And then brightness and density actually refer to the same quality attribute, but are defined differently. Brightness is the amount of luminance of your monitor. And then density is the amount of overall blackness on the processed image on a piece of film. So these two things mean the same. So when I talked about density and your mass component to make sure that you have enough X-ray to go through the body part and reach your image receptor, we talked about it in the term density. Well, in digital speak, it's actually brightness. But you have to have the correct density for it to appear on the display monitor that you're looking at. So it's still monitored or it's made by your mass that you use, but remember these two terms. So you may see density sometimes, but what we're talking about is the overall blackness. You can change the density on your monitor, but when you do that, you're actually changing the brightness, okay? An area of increased brightness viewed on a computer monitor shows a decreased density. So that would be over here on a film image. So an area of decreased brightness has increased density. Okay, increased brightness, brighter, is a decreased density, and then decreased brightness, and I'm trying to point right here where it's a little darker right there, then that means it has increased density. A radiograph must have sufficient brightness or density to visualize the anatomic structure of interest. So this is what, if this were a film, you would say it has appropriate density. I can see the femur, I can see the knee, I can see the patella, I can see the tib and the fib, and it appears maybe they left their pants on and we have some lines coming across here. Don't really need to see those, but I think they're there, and it just gives you an idea that that's what we're talking about. Now, here's an example. A radiograph that's too light has excessive brightness or insufficient density. So here, this is a knee x-ray. So let's just go back here real quick. See how this one's nice? You can see all those different components. This knee, I don't see the patella. I see where it's supposed to be, but I can't see the bony detail the way I should. And so this is insufficient density, and this is a radiograph. And then over here, that's too much density. It's too dark, has insufficient brightness or excessive density, and you cannot well visualize that knee. So if this were film, both of these would have to be repeated. This one with more technique, this one with less technique. If these were digital, the brightness in them could be adjusted, but as you know, if we were to adjust this one, we really didn't have enough exposure to begin with, so then you're going to come up with this really awful thing called noise. And then this one, you have overexposed your patient, but at least you don't have to repeat it now. So each of them have their own ways about them, but just know, the reason these images are too light or too dark is because of the exposure factors that we've already discussed. If we do not use enough radiation and we expose the image receptor, it's too light. And if we use too much exposure, too much radiation makes it to the image receptor, then the image is too dark. Again, if it were digital, we could process it and correct those mistakes. But you're still not using the correct exposure factors that you should have started with. So what is the controlling factor for brightness or density? The radiographer must evaluate the overall brightness or density on the image to determine whether it's sufficient to visualize the anatomic area of interest. He or she then decides whether the radiograph is diagnostic or unacceptable. The primary factor that affects the amount of brightness or density is the amount or quantity of radiation that reaches the image receptor. What's our quantity? Mass. However, the quantity of radiation reaching the image receptor has less effect on the brightness of a digital image because of the computer processing. When we talk about film screen, the quantity of radiation has a direct effect on film because it's done. There's no way to fix that. You can't take some back, you can't add more to it. So, in order to evaluate all attributes of the perfect radiographic quality, such as contrast and sharpness, you must have enough density to begin with to visualize the anatomic area of interest. So if you don't start off with the appropriate density, then you cannot determine whether you have a quality radiograph when it comes to recorded detail, sharpness, and other factors. So then that moves us into contrast. In addition to sufficient brightness or density, the radiograph must exhibit differences in those brightness levels. So the differences in those levels is what makes contrast. And that's what differentiates among anatomic tissues. So if you have that knee x-ray that's too white, well, you can't tell the bone from the skin. And if it's too dark, you also can't tell the bone from the skin. So the range of those brightness levels is a result of differential attenuation of the x-ray photons. An image that has sufficient brightness or density, but no differences among them, appear as a homogeneous or homogeneous object, and this appearance indicates that the absorption characteristics of the object are equal. If by some weird chance you only wanted to take an x-ray of someone's arm, but you only care about the fat part of the tissue and not the bone, you may get something that looks like that. That image right there is homogeneous. That means there's nothing in there that varies in its thickness or its density or subject matter. So when you have an image like that, then that means there's nothing there to x-ray. But that's not what we're looking for. We're looking for something that has different density so that we have contrast. So radiographic contrast is the combined result of multiple factors associated with the quality of radiation. It also has to do with anatomic structure, the image receptor, and in digital imaging, the processing and display of the computer. The quality of the X-ray beam also affects its attenuation in tissues, which alters subject contrast. And what is all of this? Increasing the penetrating power of the X-ray beam decreases attenuation, it reduces absorption, and it increases X-ray transmission. And that means there's fewer differences in brightness. And what is quality? KVP. So the KVP is that exposure factor that we've already talked about that you need to know how to use appropriately for the body part that you are X-raying. Subject contrast refers to the absorption characteristics of the anatomic tissue that we radiograph and the quality of the X-ray beam. Differences in tissue thickness, tissue density, and the atomic number contribute to subject contrast. Brightness or density is easily measurable. However, contrast is more complex. When we try to evaluate radiographic quality in terms of contrast, it's actually more subjective. It has to do with the individual that happens to be looking at that radiograph. The level of radiographic contrast defined in an image is determined by the composition of the anatomic tissue and the amount of information needed to visualize it for an accurate diagnosis. I can tell you that in my years of experience, when it comes to contrast, anyone who's been in the field more than 10 years prefers more contrast. They like that black and white image. The newer technologists, because they're more familiar with digital, they are more used to the grayer or a less contrasty image. And there's nothing wrong with either one as long as whoever your radiologist is, when you take that film, You've done it the way they want it, because they're the ones to read it, stamp it, and put their name on the bottom line. So here's another area of looking at contrast. When the absorption characteristics of an object differ, it has varying levels of brightness or densities. The anatomic tissues are easily differentiated because of these differences in brightness or density. So this is just that same fake image, but now we've thrown a couple of things on here. Tissues that attenuate the X-ray beam equally are more difficult to visualize because the brightness or densities are too similar. And so to differentiate among them, there must be density differences. So density differences means the image's radiographic contrast. So here we have something that's white, gray, darker. Those differences make them contrast with one another, and they are different densities. Density differences are results of the tissue's differential absorption. So this is just an image of different objects on the same thing. This is a fake bone, and who knows what these are. It doesn't even say in your book. You know, this comes from, it's in your textbook if you want to look at it, figure 9.6, but it doesn't tell you what they threw on there. But now you can see the contrast of those. The chest is composed of tissues that vary greatly also, and so the chest x-ray is one that's really nice to look at because we have air, which is going to show up as almost black. Then we have fat that's kind of gray, and when we say fat, we're not talking just obesity fat. Any type of skin that's out here is more gray. And then you have bone, which is basically white. So here we have clavicle, we have ribs, we can see the spine coming through here, we can even see the heart. Why does the heart have a shape on here? Because it's made out of water, and that's different from the air that it's in. So your same x-ray went through all these three different tissues, and so they all look different on the film. And this particular area, this region in the body creates high subject contrast because the tissues attenuate very differently, and that would be different for an abdomen. So, you know, the air-filled lung, the heart full of liquid, and then the bony thorax. This is a very contrasty film. And it's not as contrasty as, say, some extremities, but just because you have this black and then this white and then this gray. Now, when we compare that to an abdomen, look how these are closer together. Now we've left off the bone because the bone still shows, but now we're really looking at the abdomen portion here. So this is the small intestine, maybe you can see a little of the stomach here, and you can still see bone. But the abdomen is different in tissues that attenuate the beam similarly and is considered to be a region of low subject contrast. The brightness or density representing organs are more similar. So this is going to be the level of, you can see the liver, not really, but you can see how it makes it lighter here. The spleen is going to be a little higher, so it looks different there, you know, and then you can't see the stomach from the kidneys because they all just kind of look the same. So this is what you consider a low subject contrast from fewer differences in radiation. And so your muscle, your water, and your fat's about the same. Okay, so that covers a lot of the photographic properties of X-ray. Next we'll look at geometric. All right, geometric properties. Now that we've looked at the photographic properties, let's look at geometric. And this has to do with the sharpness of the structures and whether or not we can detect the smallest object in the image. And I'm going to go ahead and throw this up there because I know these are seashells, and you're going, well, that's not what I x-ray every day. But when you look at this x-ray, okay, if you've never seen a starfish, look at these really cool little areas of that starfish. And if you blew this up, you can actually see the different spines of each one of those, and then these shells and how they're different. This is a different shell, and it's not just the way it's shaped, it's the density of each one of these that makes them different. If we have the appropriate exposure factor, then we can see the sharpness and the spatial resolution of all of these different attributes of these shells. Now we also are concerned about distortion, and that's in two types. You have size and shape. And did we magnify the part by mistake? Is the shape correct? You know, just like the anatomic area of interest is supposed to be. And those are the things that we're going to talk about now. It's a shame we can't just X-ray shells it, isn't it? That's pretty. Okay, here we go. The quality of a radiographic image depends on both the visibility and the accuracy of the anatomic structural lines recorded, and that's called sharpness. Adequate visualization of the anatomic area of interest, which is brightness, density, and contrast, is just one component. To produce a quality radiograph, the anatomic details must be recorded accurately and with the greatest amount of sharpness. So to obtain that perfect sharpness, we look at three other components, and that's resolution, spatial resolution, and recorded detail. And we'll talk about, you're going to say, well, resolution and spatial resolution, they're actually two different things, okay? So let's go through all of those. The first is resolution. Resolution is the ability of the imaging system to resolve or distinguish between two adjacent structures. So if you have two things sitting side by side, when you take that X-ray, you need to be able to see on your X-ray two different things. It can be expressed in an actual measurement, and that's line pairs per millimeter, and you'll see right there, LP/mm. That's what it's expressed in, and so this is a resolution test pattern that is used to record and measure line pairs, and the greater the number of line pairs per millimeter, that means the greater the resolution. So if you look down, as you go down here, then this is line pairs per millimeter. So look how thin these are. You can just see, and these are all, and now we're not looking at the black part in between, we're looking at the line pairs. How many line pairs can you actually see in there? And this is actually shown a little better in your textbook, but that just gives you an idea. But the higher number of line pairs, that means the greater the resolution. Now when we look at resolution, that's just in general, two structures side by side. Now we have something called spatial resolution or recorded detail. Spatial resolution refers to the smallest object that can be detected, and that's what we use in digital imaging. So resolution in general is, spatial resolution is the ability to see the smallest object. And then recorded detail is also the distinctness of structural lines, but we use that term in film screen. So even though resolution in general is how well we see two separate objects, when we go to spatial resolution, we're talking about being able to see the smallest. Now, we're only going to cover the digital components of this, so you may or may not see recorded detail again, but know that it's the same as spatial resolution. In the space of 1 millimeter, so if you can imagine how small 1 millimeter is, the number of line pairs resolved determines the amount of sharpness. Each line pair is made up of a line and a space. Then an imaging system that can resolve fewer line pairs within 1 millimeter is said to have decreased sharpness. So you want one that can actually identify more line pairs. The ability to discern small changes in spatial resolution when we view a radiographic image depends on the visual acuity and distance of the viewer. So even though we may give the best image possible, it also depends on who's reading it and if they can see that very well. The ability of a radiographic image to demonstrate the sharp lines determines the quality of the spatial resolution, and it's impossible to produce an image without some degree of unsharpness. So you're going to have a little bit of unsharpness there. But we want more spatial resolution so that we minimize unsharpness in the anatomic structural lines. Okay? And then this is just a blown up area there that shows there's our airspace, there's a lead strip, and then these are our line pairs. So how many of these can you see in 1 millimeter? And that's what spatial resolution is. Now, when we come to sharpness, sharpness of recorded detail and visibility of recorded detail are usually two separate qualities of an image. And generally this separation is true except when it comes to small anatomic structures. A small anatomic structure is best visualized when its brightness or density varies significantly from the background. If unsharpness is increased, the visibility of that small detail is compromised. So you have to think about, and again, I know none of you have gone to clinical yet, but imagine that you are looking at someone's shoulder and you want to see where the clavicle and the acromion actually come together, and if there's a tiny little break right there, you need to be able to see that smallest detail. It has to do with the factors that you use, the image that you take, and then the ability for the monitor to see it. Now, what's even better about being able to see in the digital world is they even have something called a magnification view, where just like on your computer, you can magnify it up so you can see it bigger. The resolution may not be as good, but you can actually see it. With a film, you're stuck with that film the way it is. So if unsharpness is increased, the visibility of small detail is compromised. So the spreading of the structural lines with increased unsharpness decreases the densities or the differences in brightness or density between them. So the difference in brightness or density between the area of interest and the background becomes less and the visibility is reduced. This image is also in your book, and if you want to look at it right here, so this is what we're looking at. This is the object point. This is little unsharpness, and there's your image, and so your contrast is 100%. This is white with a black background, so you see it. But right here is the unsharpness. Because of the contrast, you're only getting 50. See how that's checkered in there? And then this one is even checkered more. So this is just showing you what sharpness means. We want it to look like that, but the only way we really can see it that well is if it has a difference in the background. Okay? A radiographic image cannot be an exact reconstruction of the anatomic structure. You're always going to lose a little bit of the information during the processing. In addition, factors such as patient motion increase the amount of unsharpness that's recorded. It is the radiographer's responsibility to minimize the amount of information lost by manipulating factors that affect the sharpness. Diagnostic quality is achieved when you maximize the amount of spatial resolution or recorded detail and you minimize the amount of image distortion. So again, it has to do, if you have patient motion, then it's up to you to catch it either when they're not moving or make that image so quickly that you miss the motion. So this is also in your textbook, figure 914, and it shows patient motion. So here you say, well, I can still see the lungs, I can still see the spine, and it's a good lateral chest x-ray, but that little bit of motion has made it unsharp. I like to use the word crisp. This is not a crisp looking x-ray. You want to see this line here without smoothness. It should actually be a contrasty line between this area and the rest of the body. So you have to be very careful with that. All right, now let's go into distortion. Distortion results from the radiographic misrepresentation of the size or the shape of the anatomic part. When the image is distorted, then you get spatial resolution or recorded detail is also reduced. Now, I didn't put recorded detail because that's the film word. So spatial resolution is what we're talking about with digital. The term size distortion is also magnification, is when there's an increase in the image size of an object compared to its true size. Radiographic images of objects are always magnified to a degree, and of course what changes that has to do with source to image receptor distance, the object to image receptor distance, and the other things that we've already discussed before when it comes to exposure factors. Because radiographers produce radiographs of three-dimensional objects, some size distortion always occurs. And so the parts that are further away from the image receptor are going to be radiographically more distorted than parts that are closer to the receptor. So we have to keep that in mind, and there's not much that we can do with that, okay? Objects that are being imaged can also be misrepresented by distortion of their shape. And that is, it can be elongation or foreshortening. And so those are the two types of distortion, again, that take it away from the true anatomic appearance. So that's what we call distortion. You can go back to the chapter that it was in before, look at the formulas and how to do that. So here though, and that was with the magnification, here are some quick review images of shape distortion. This is a no distortion of a bone. Now notice that bone's not attached to anything, so it's just a model. But this is the same bone, and it's taken, and that's called foreshortened. It's made shorter. Now not only is it shorter, you could actually measure it here, but notice how much larger the ends are, and that's because there's been some type of distortion with either the body part, the tube, or the receptor. And then this one is elongated. Now we probably elongated it this way because this is bigger down here and this is smaller, so the things that are further away from the tube are going to be a little bit elongated. How does this happen? You either have misalignment of the central ray, so this would be correct, and then this one's shortened, and then that one's elongated. And so then, well, these are both foreshortened, and these are both elongated. You can also have the tube, the part. Sometimes shape distortion is used on purpose for particular projections and positions, and you'll learn about those later. But when this happens and you did not intend for it to be, then that is just called distortion. So this is an important component in digital and film. Now we're going to be more concerned about the digital, but you need to make sure that you understand it can happen in either way, so do your best not to. Here's a quick thing on the magnification, just because it was there. If you have an object and your source to image receptor distance is too great, it's going to be greatly magnified. You know, you can go back to chapter 10 and look at magnification and shape distortion. But those are the things that actually affect having a quality radiographic image, which is the content of this particular chapter. So let's go to another one. We had a whole chapter on this one too. Scatter. Scatter radiation can add unwanted exposure to the radiographic image as a result of Compton interactions. Unwanted exposure, or fog, does not provide any information about the anatomic area of interest. In fact, it degrades the visibility of structures. The scatter or unwanted exposure recorded on the image actually decreases contrast by masking the desired brightness on the image and changing the degree of differences. Fog produced as a result of scatter can be visualized on both digital and film images, and even though the computer can change the contrast or gray levels, you need to know that the digital is actually more sensitive to scatter, and that's because the digital image receptor can detect those low levels more so than the film did. So knowing how much difference there is, this is less scatter and this is more scatter. And both of these were taken on a digital system. And you just cannot get it to go away no matter how hard you try. But we want to see this bony detail here in this femur, which you're not getting because of the scatter there. Now, when you're trying to change all of these factors and make that quality image, you have to remember too that image noise contributes no useful diagnostic information, and it detracts from image quality. Quantum noise is a concern in digital and film because it's photon dependent. However, in film language, you actually have, there's fewer photons, greater noise, but in film, the word is called model. Now, in digital, we go with the word quantum noise because noise is a digital term. And if you look here, and this may be hard for you to see as well on this presentation, but look in your book, it's figure 917. So this is appropriate. Over here we use the right amount of exposure. So we see this nice black and white and some grays. But over here there wasn't enough exposure, so the computer processed it to make it look good, and in doing so you get this noise in here. There's a good example of it right there. Okay, so now that we've talked about brightness, contrast, shape distortion, size distortion, scatter, and quantum noise, let's look at another thing that actually affects the image quality of our radiograph, and that's artifacts. An artifact is any unwanted image on a radiograph. Artifacts are detrimental to radiographs because they make visibility of the anatomy or pathology or patient identification information difficult or impossible. So if you have an artifact that covers up any part of the anatomy, it's possible it's covering up some pathology. And what if you have actually covered up the name of the patient or something else that identifies that patient? It also decreases the overall quality of the image. And there are several different methods of labeling artifacts. Generally, they can either be a plus density or a minus density. And it's exactly what you think. Plus density means there's something dark on your image that shouldn't be there, and a minus density means there's something white on your image. Plus density or greater in density than the area immediately surrounding them, and minus density is when it's less density than the surrounding areas. And in those artifacts, scatter or fog or noise can also be classified as an artifact because they add unwanted information on the image. Now, here's an image that you need to understand. This is an artifact on that image, but guess what? That's not an artifact that you can change because this is actually a pacemaker. So the first time that you get a chest x-ray and you see this, it's not like you can ask that patient to take it off. This is actually inserted under the skin in that person's chest. This is the control, and then these wires are actually going to the heart. And in fact, you will do lots of these x-rays so that they know that the wire is going exactly where it's supposed to be. And so this is an artifact that is not necessarily unwanted. You need this. So this is different from other types of artifacts. So when we talk about an artifact, it's something that you do have control of taking off or not having on your film. Okay? So let's make sure between those that you understand the difference. So errors such as double exposure or an improper use of equipment can result in an artifact. Those two things, double exposure is just that. You took an x-ray, you didn't process it, and then you took another x-ray on that same plate, and then guess what? You've got two exposures on one film. That's an artifact. You can't have that. Then you have a foreign body. Now, a foreign body that can be removed, that was up to you to take it off before it happened. But I also want to point out here that sometimes you may take an x-ray to find a foreign body, and that's when it's classified that you're identifying that foreign body. So don't get those confused either. When you have a patient that comes to you, and let's just say it's a hand, and sometimes they'll ask you to x-ray a hand to find a splinter or a piece of glass or a piece of metal, doesn't matter what. You're trying to identify that artifact. You may need to adjust your techniques to fix that. But if you take an image and you've been too lazy to take their clothing off, you get a different type of artifact, and that particular artifact happens whether it's film, digital, however it is that you take that image, because something like this, that's your fault. This is someone who has a chest x-ray and they didn't ask them to take their necklace off. Now, even if they were in a t-shirt and you saw that t-shirt, you should have been able to see that necklace. So that is an unwanted artifact that it was up to you to remove, so you would have to repeat that exam. Now, I will tell you, in the day, and it's possible even now, depending on what that person came in for, although personally I'd retake it too because you've clipped the edge of this lung right here. So there's two things going on there. But that particular artifact, the radiologist may want you to take it over, or if he's only looking at the mediastinum and he says that doesn't bother him too much, he may let it go through. But those are the kinds of things that you have to worry about. And so when it comes to artifacts in general, it's anything that's unwanted, and we're going to look at some of these others, the double exposure, the equipment misuse. And again, when you're looking for a foreign body, that's something that you are looking for to define where it is so that they can go in there and take it out. Dr. Stuart Bashong is a well-known physician. Well, he's not a physician. His degree is in radiology physics, and he's a very well-known scientist. He's a physicist, and he has produced books for years and years, and I believe his is available in the library if you'll ever want to read through his material. He has a whole lot of different things in his material that could be helpful, and some of it may not be necessary, but it's there. This is from his textbook. I just want to make sure you understand that's from him. It's also an Elsevier product. But he classifies his digital artifacts into these three areas. You have an image receptor. So your image receptor, where the latent image goes, could have dust, dirt, scratches. It can have a pixel malfunction, or it could have a ghost image. You can also have software artifacts. Histogram, scaling, range, image compression. These are software. So that's the computer. Then you have the object artifacts. You position the patient incorrectly, you didn't collimate correctly, or you have some backscatter. And I think that's interesting. He doesn't even throw the other artifacts because you shouldn't let those go through. But anyway, so those are three different areas that you could consider them in. There's nothing that's like written in the ARRT that says they're in those areas, but it'd be worth you knowing which one was which if you ever have to come across something like that. So from our textbook, we have just digital artifacts, and the ones that they really talk about are digital image artifacts can be a result of errors during extraction of the latent image, and that makes sense. I mean, let's go back here. So when it has to do with the receptor artifacts, any of those can be part of it. Inadequate erasure, and that's probably a software artifact. And then inadequate CR imaging plate and performance of the electronic detectors. So all of those are the ones that we're classifying as digital artifacts. And although it's not part of this discussion and you won't have to know it later, these are the artifacts that had to do with film. They were usually film storage, how you stored the film in the darkroom, how you handled the film, or how you processed the film. You're not responsible for those, but I just threw them in there so that you can see the differences in how things have changed over the years. So now we're talking about extraction of latent image through an electronic detection. So much different from shooting a film, sending it through a processor. So here's one. Debris on an image receptor in digital radiography could be confused with a foreign body. So now, number one, what I want to really point out here is this is a child's hand. And how do I know this is a child? Because all of the bones have not actually formed yet, and they're not connected. So you don't even have all the carpal bones right here. But when you look at this, you could go, oh wow, this kid's got a piece of metal right here, and oh, there's something right there. Well, it actually is just an artifact, and you may not have even noticed until I pointed it out, but that turned out to be debris on the image receptor. So when you have this come up, the first thing you need to do is say, first you look at your patient, say, have you had any injury, and see if that's a real artifact on the patient. And then if it's not, that receptor needs to be clean before you take another image. But you may have to repeat that to prove that it's not in the patient. Because if the radiologist read that as a foreign body and it's not one, somebody might decide to take the kid to surgery. So, those kind of things are very important. Now, this is another one. Now, I've already given you the answer up there, but it turns out to be glue in the CR. Now, in your labs the week before this, you've already talked about CR and DR. CR is computed radiography, and with that, you have a plate that you actually put in to the table, and then you run it through a digital component. And in case you didn't see it when I first popped it up here, there's the glue right here. So it's this line. But even that line, most radiologists would know that that's not in the patient, but you may have to take something out just to make sure. So with that, the residual glue on it resulted in an artifact, and they actually had to take that plate out of service so that it wasn't used again because it couldn't be cleaned. Now, while I've got this image up here, though, I want to point out these are EKG leads. Now, these are on the outside of the body of this person, and you do not. Even though I said if you can remove it, you should remove it, things like this you do not remove because that may be monitoring more than what you need to deal with that patient. So the radiologist knows these are EKG leads, so don't worry about that. And then I want you to notice this little thing right here. This is where they have had a tracheotomy, and so they have actually got a breathing tube in their trachea. So that's something else you could not remove. So those are types of artifacts that are there for a reason, and you don't have to worry about them, okay? But this down here is bad because, and especially if it showed up, you used it on 3 patients and it's in all 3 patients, then it has to be taken out of service because it affects your quality. Here's a double exposure. Now, when you look at this, and I know y'all are still new to imaging, but you see a chest x-ray, right? Well, when I throw this arrow on there, look at this. This is actually the ischium of a pelvis right in here, and then this is bowel gas. So this is actually a pelvis and a chest x-ray that was taken on the same imaging plate, and it was not fully erased before the chest was taken. Something like this you would also have to repeat. Now, because this is a double exposure and they said it wasn't erased, the pelvis is probably okay and it's already been sent for processing, but this chest x-ray will have to be repeated because it's got stuff on here that doesn't belong to this patient. So think about that. Then this is a damaged CR plate. Now, I took this from Bouchong's book, so it was already put together. But if you notice this right here, the white shape's on the left side, and when they took this and it showed up, it turns out this is the CR plate and it was actually damaged. And because it was damaged and peeling off like this, that's what caused, it's like having a light in there when they took the x-ray. So they had to take that one out of service too. So these are all some artifacts that you could potentially see in your future and just know what they are and how to rectify them. Now, these are processing failures or processing artifacts, and you may or may not be able to notice this, but this is supposed to be well, it just says failure of electronic pre-processing can cause uninterpretable. Yeah, I mean, I know what this image is, but it's useless. There's nothing that could be extracted from it. But they're saying it happened because of a processing error. That was your computer error. Nothing that you did was wrong, but it will have to be repeated. So that's something that you have to worry about with digital. And then this is a raw X-ray beam, and it has a Hill effect response. Now what they've done right here, so here's the anode and cathode sides, what they're showing you here, and they've done a flat fielding pre-processing, can make it more uniform. Again, this is not something you will have to actually work out, but what if this was an image that you took and that's what you got instead of the body part, okay? So know when something doesn't look right. And then this is an image produced by background radiation on a CR plate that had not been used for days. And this is something else that we will talk about later, is that when you have a CR plate, and that's computed radiography, if it's been sitting around and not used, the person coming in first thing in the morning is supposed to erase them. You can erase every plate after it's been sitting around for a certain length of time. So what they did is they just ran it to see, and this is just exposure from sitting around gathering some remnant X-rays that have shown up. And then here's an underexposure. This is digital radiography, causes loss of contrast because of increased noise. And so they're showing you this histogram right here. And so this was underexposed, and what they try to do is go ahead and create an image from it, but it just doesn't work. So that would have to be re-exposed. This is another thing, and this also has to do with the processing. These were two plates used for spine imaging, but they were put in the processor in the wrong order. So you will find when you actually put them into the reader after you have taken the X-ray, then you say this is an AP spine. So then it has a certain histogram that creates the image from what you've told it was. But what they've done here is they've put the wrong things, so these are no longer usable. So just some more of those digital artifacts. Now, digital imaging possesses a number of unique qualities that distinguish it from film screen, and that is, one of those is that it can respond to a wide range of exposures. So that's called wide dynamic range, and that's one of the most unique and the most beneficial part about a digital image. You can use more exposure and still have a quality radiograph because the computer fixes it. But we do not want to overexpose. We want to use exactly what we need. Anatomic areas of widely different attenuation, such as soft tissues and bony structures, are more easily seen or visualized because of that wide dynamic range in digital imaging. In addition, because of computer processing, moderately underexposed or overexposed images may still be acceptable diagnostic quality. Digital images are composed of numeric data that it can be manipulated by the computer, and when it's displayed on the computer monitor, that it allows flexibility in terms of altering it, and that helps you alter the brightness and contrast as well. So the practical advantage of all of this is that regardless of the original exposure parameters, within reason, that any structure can be independently and optimally visualized. However, we never want to overexpose something because we want to make sure that it's where it needs to be before you actually take it. And your computer can do so much, but that's it. Now, when it comes to taking that digital image and recording it and then creating the image out of it, we have to talk about something. It's recording on a matrix, and that's a combination of rows and columns, and usually small square picture elements called pixels. And believe it or not, you may actually be asked one day, what is a pixel? That stands for picture elements. So a recording matrix is made up of a bunch of pixels, and each pixel is recorded as one single numeric value, which is a single brightness level on a display monitor. And the location of the pixel within that matrix corresponds to an area of patient volume of tissue. For any given anatomic area, a matrix size of, so what we're saying is the the matrix itself is made up of a certain number of pixels. So if you have a matrix that's 1024 by 1024, then you have 1,048,576 pixels. But if you bump it up to a matrix of 2048 by 2048, you get up to 4 million pixels. And we're going to talk about how each number of those makes a difference. So your matrix is always the overall, whatever it is that you took. So this is the size of it. And this happens to be a KUB. How many pixels within that matrix determines how your image will actually look. That's the basic way of saying that. Alright, so with this digital image, it's made up of a matrix of many small elements or pixels. So this gives you a little bit better visualization. And by the way, these images are from sprawls, which are also available to you on Blackboard, so you can look through those. Each pixel is represented by a numerical value, and in general the value is related to the brightness or color. So I've just said that a while ago, but at the time of viewing, the actual relationship between the pixel's numerical value and its brightness. So every pixel has a specific brightness to it. So it can be anywhere from white to black, any of those varying shades of gray. Then its display determined by the adjustments of the Windows control, and we'll talk about those window controls later. So it's really no different from this image, but what I'm wanting you to see here is that every single one of these is assigned a brightness or a color value. And it's not just black or white, it can be any shades of gray, okay? Now, when it comes to what you need to know for like our quiz, for our exams in this class, and then for the registry, you need to know that a digital image is composed of a matrix that is made up of a certain number of pixels. Now, your pixels then, here's some other words. The numerical size is the number of bits. 8 bits equals a byte, and we don't go into a lot of this detail in the textbook that we have because it's assumed that you already know that, but you need to make sure that you do know these. And this is the product of two factors, and that is the matrix, the pixels, and then the bits. So how many bits per pixel? 8 to 16 bits, 1 to 2 bytes. So for every pixel, you want to know how many bits make it up. 8 bits equals a byte, and then here's our matrices. And then notice these are the two that I gave you earlier. Well, if you only have a matrix of 128 by 128, you only have 16,000 pixels. So the fewer pixels that you have, it's still filling the same size area, so these pixels are larger. And then down here, these are smaller. So there's smaller pixels, so that means there's more of them, and that gives you a better picture. So let's go on to the next one here. Digital imaging quality is improved with a larger matrix that includes a larger number of smaller pixels. So it's more of them, but they're smaller. Although quality is improved for a larger matrix size and smaller pixels, it's also important to understand processing time, transmission time, and storage space. All of that will also increase as the matrix size increases. If you increase the matrix size from 1024 to 2048 without changing the image field, it will produce smaller pixels. So you have to think about this. Here's a large matrix, here's a small matrix, and this one is going to, but they're smaller pixels, these are larger pixels, so you have the same number. So if you don't have the same number, you have more, and the pixel sizes are smaller, and it's going to look better. Okay, so here's another way to look at it. These are in your textbook. 920. For a given field of view, the larger the matrix size, the greater the number of smaller individual pixels. Increasing the number of them improves the image. So this is a 64 by 64. And what do you think about that picture? It's pixely. You can actually see the little boxes in here, and it doesn't look very nice. So what we've done is bump this up to a 215 by 215. Well, it's a little better, but I can still see some pixels in there. Now this one's on up to a 1024. This is actually not so bad. Now this is the same exposure factors used with the same X-ray, and all you're doing is processing it with a larger matrix. So this is the largest matrix, and this one's a 2048, and it's even better than this one. And all it has done is, because it's bigger, it has more smaller pixels in there. When you think about processing this digital image, the numeric value assigned to each pixel is determined by the relative attenuation of the X-rays that pass through the corresponding volume of tissue. Pixels represent highly attenuating tissues such as bone are usually assigned a low value. A low value for higher brightness, lower density than the pixels that represent tissues of low X-ray attenuation. So if you have high attenuating tissues, it's a low value, so that's going to be a whiter. If it's a lower attenuating, that means it absorbs it, then it's a higher value. Each pixel also has a bit depth, or number of bits, that determines the amount of precision in digitizing the analog signal, thus controlling the exact pixel brightness that can be specified. So the larger the bit depth, the more shades of gray that's available. Bit depth is determined by the analog to digital converter that's a component of every digital imaging system. A larger bit depth allows greater number of shades of gray to be displayed on a computer monitor. For example, a 12-bit depth can display 4,096 shades of gray, but a 16-bit depth gives you 65,536 shades of gray. So you want a larger bit depth so that you can have more shades of gray. And a system that has a greater number of shades of gray can give you better contrast resolution. And that's the bottom line here. So when you talk about a digital image, you want more shades of gray. This goes back to just as simple as if you have a television. You know, don't you want more, the higher the number, that means the more pixels that you have, and they're going to be smaller, so you have higher resolution. And to get a high resolution TV, it has all of these words that are built into it. I can't even go into it how it works, but I know that you know, I remember looking at a TV when it was still kind of grainy, and so the improvements that made over the years is the same with our X-ray. The improvement of digital imaging has just created so much more. So here's the matrix of pixels, here's the bits, you know, and then they go into a picture there. A digital image is represented in the imaging computer system by numbers in the form of binary digits called bits. So there's another one. If somebody asks you, if you see a test question, what's a bit? That is a binary digit. Here we see the general structure of a digital image. It's divided into a matrix of pixels, and then every pixel is represented as a series of bits. And if you see here, you see all these little numbers. Then we actually look at the issues that affect the number of pixels in an image and the number of bits per pixel, the so-called pixel bit depth. Boy, those are hard words to say. So here is also in your textbook, and these are your pixels. So this darker pixel is decreased brightness, this one's increased brightness. So that's black, that one's white. And with that different volume of tissue that's imaged, it has to do with how long it took the X-ray to go through the body to produce that. This one hit it quickly because there's nothing over there. This had to go through bone, so it absorbed a lot, and that's why it turns out white or increased brightness. decreased density. Okay, you got it? Those are backwards. So when it comes to digital image pixel bit depth, if you had 1 bit per pixel, this is what your chest x-ray would look like. But adding up to 4 is a little better. And then if you're going up to 8, and then look here, you know, that's how many shades of gray. So with 8 bits per pixel, you get 256. We're working with equipment that has so much more than just 256, and that's important too. Okay, that's about all for the display of it. Now let's go on to intensity. Visibility and accuracy of the anatomic structural lines recorded are equally important. However, you need to know that intensity does not control the amount of brightness produced on the digital image. So when we talk about the intensity of the exposure that reaches the receptor, it doesn't control the brightness, okay? So you're more concerned about using the correct exposure factors for the specific body part so that you can get a quality radiograph. Digital imaging characteristics. Now, we've talked about each one of those in general, but now let's just do them quickly of how you actually see them once they're done. So this is brightness, contrast, spatial resolution, and noise. Brightness. In digital imaging, the level of brightness displayed on the monitor is important. Because the image is composed of numeric data, the brightness level that's displayed on the computer can be easily altered to visualize the range of anatomic structures recorded. The X-ray beam that exits the patient, remnant radiation, hitting the image receptor as a latent image, has a wide range of X-ray intensities. It often varies by more than 1,000. To adequately capture these intensity extremes, you have to have a receptor with a wide dynamic range. Because digital imaging provides a wider dynamic range than we'd had in film screen, and the computer can adjust for errors, there is a greater margin of error for exposure techniques. And because digital imaging processing can compensate for those errors, the digital image may display the appropriate level of brightness, but be over or underexposed. Therefore, you, the radiographer, may be unaware of that exposure error, but you should be aware of it because you should always use the appropriate factor for the body part and for what it is that you're wanting to x-ray. Okay? But a digital image system will actually make it better for you. An important feature of digital imaging is the exposure indicator. The exposure indicator provides a numeric value that indicates the level of exposure to the receptor, and that's what an exposure indicator is. A numeric value to indicate exposure to the receptor. So what you started with, what went through the patient, and what hit your receptor is going to come up as an indicator. Currently, they are not standardized among the various digital equipment. However, industry is working to change that because right now there's so many different ones that it can be a problem. No matter where you are, what equipment they have, you are responsible for seeing what your EI, your exposure indicator, is and how it actually matches, or if it doesn't match, what your range was supposed to be. Okay, so that's very important. Now, I found this, and these are just the 3 top ones. So if you have, look at this one. Exposure indicators are even called different things. So Fuji and Konica use something called an S number, and that's sensitivity. And its value for 1 milliröntgen is 200. So your 200 is what you're always looking for. Now, here's something that's even stranger. If your double If you're 2 times more than it should be, your number goes down. And if you're only half of what the number should be, it goes up. Carestream or Kodak uses an exposure index. They're the only ones that actually has a true EI. And its value is around 2000. If you're make an exposure using too much, 2 times that exposure, your number is going to be 2300. And if it's half, it's 1700. So that means it varies by a factor of 300. And then AGFA uses something called a log median value, and the value for 1 milliroentgen is 2.5. And if you're double the exposure, it's 2.8, and if it's half, it's 2.2. So this is also an exposure difference of 0.3. So interestingly, both of these use 3, but in different ways. So, and you don't have to memorize that. I just threw it out there to show you they're not standardized and they should always be evaluated. So, you know, having the knowledge of what you are currently working on is the most important. Once you start going to clinical, you may go to 5, 6, I don't know how many different clinical sites you'll go to, but each one of them may have a different type of unit. And that's one of the first things you're going to find out. Okay, if I do a tib-fib x-ray, what is my exposure indicator? They're going to have it somewhere there for you. And we'll go over this more in the next quarter, in the next course, okay? So let's go to optimization. A wide dynamic range is only useful if you can optimize it for human perception. This adjustment is accomplished using something called windowing. So when we actually take a digital image on our monitor and we want to make it right, we window it. The window level, or the center, sets the midpoint of the range of densities that are visible, or brightness for us. Changing the window level allows the image brightness to be increased or decreased throughout the entire range of densities. So when you change the window level, everything either gets brighter or darker. When the range of densities displayed is less than the maximum, the processed image presents only a small sample of the total information contained in the computer. So know that window level is brightness. Okay? LB is how I always think about that. Window LB, and in case you didn't know, LB stands for pound. So window level brightness. And then here's your adjustments. Assume the pixel values range from 0 to 2048 are used to represent the full range of digital image brightness levels. A high pixel value could represent a volume of tissue that attenuated fewer X-ray photons and is displayed as a decreased brightness level or increased density. Therefore, a low pixel value represents a volume of tissue that attenuates more X-ray photons and is displayed as increased brightness or decreased density. So if you move the window level up to a high pixel level, it increases the visibility of darker anatomic regions. So this is where you'll see more chest or lung fields. And conversely, if you move your window level down, then you would decrease the window level to decrease the brightness. Okay? Whoops, sorry. There we go. But that's all in your textbook also. So the window level up or down has to do with brighter and darker regions of interest. Now, when it comes to contrast resolution, the number of shades of gray that can be stored and displayed is called grayscale. Contrast resolution is another term associated with digital imaging, and it's used to describe the ability of the imaging system to distinguish between similar contrast objects. And an important distinguishing characteristic is improved with contrast resolution compared to film. So it's a good thing. The contrast resolution of an imaging system determines the level of visibility of small objects that have the same density or shades of gray. The depth of the pixel is determined by the bit depth, which we've kind of already talked about, which then affects the number of shades of gray. That increases the contrast resolution within the image. And then the image with increased contrast increases the visibility of recorded detail and the ability to distinguish among small anatomic areas of interest. So now that we're talking about contrast, your brightness was a window level, and that is the overall darker or lighter. Now we're talking about grayscale, and with grayscale we can actually determine between similar contrast objects. So an increased number of pixels increases contrast resolution, increasing the visibility of recorded detail. And what do we call that? To visualize radiographic contrast, it can be adjusted to vary depending on the area of interest. And this is necessary because contrast resolution in the human eye is actually very limited. What we can see by itself is less than what that computer monitor can show us. With this, we have something called window width. And window width is a control that adjusts the radiographic contrast. Because the digital image displays grayscale densities from black to white, the monitor can vary the range dependent on the anatomy. And then adjusting the range of density actually varies the contrast itself. And all of this is performed with the computer or display monitor. So when we look at the visualization, here is what it comes out as, but then our image brightness is black or white, but at the same time the contrast is showing us more of these gray or levels of gray in there. So then it increases or decreases the range of densities. So a narrow window width decreases the range, and that increases contrast. So this right here is going to be black and white, but this one out here is going to have a wider range, and it increases it so you get more shades of gray. Window level controls brightness, WLB. Window width controls contrast, WWC. Just keep those in mind. When the entire range of densities is displayed, that's called a wide window width. The image has lower contrast or more shades of gray. Wide window width, lower contrast, more shades of gray. When a smaller range of density is displayed, that's a narrow window width. It has higher contrast or fewer shades of gray, more black and white. So wide is a lot of gray. Very narrow is either going to be down here or up here with nothing in between. The center or midpoint of the window level and the width of the window determines the brightness and contrast, and it's important to display digital images on a monitor with high luminance. We talked about that at the very beginning of brightness, so that you can visualize the wide range of gray levels. Here's another image. This is figure 926 in your book, and this is your window selection. If you change the window level for a chest x-ray, then it varies the visibility of the anatomic detail. So here's a low window and a high window. So there you go. Now we need to talk about something called spatial resolution. A digital image is composed of discrete information in the form of pixels that displays various shades of gray. The size of one pixel is actually measured in a micron, and 100 micron is 0.1 millimicrons. As mentioned before, the greater the number of pixels, the smaller their size. So the matrix is the same size, but if you increase the number of the pixels, they get smaller. An image consisting of a greater number of pixels provides improved spatial resolution. In addition to its size, the pixel spacing or distance measured from the center of a pixel to an adjacent is the pixel pitch. So here's the center of one pixel, whoops, and then there's the center of the other pixel, and that's the pixel pitch. Oh. Different types of digital imaging receptors use varying methods of transforming the continuous exit radiation intensities into the discrete pixels for image display. And one of the things that you need to make sure you have is that you need a high resolution monitor so that you can actually take advantage of all of these different pixels that we have. So this is figure 927 in your book, and it talks about how spatial resolution is dependent on your pixel size and the pixel pitch. All right, we've mentioned this word before, but the digital computer system can adjust for low or high exposures during exposure variations with your image acquisition. So yes, if you overexpose, yes, if you underexpose, we can still create an image from that, but that's not what we aim to do. When the exposure of the receptor is too low, that means there's a decreased number of photons that actually hit the patient and hit the image receptor, then computer processing alters the appearance to make the brightness acceptable, but it increases quantum noise. And there are certain post-processing options that render more quantum noise than others. No matter what, your exposure technique should be selected on the requirements of the procedure regardless of system type. And what we're talking about is whether it's digital or film screen. And under digital, if it's CR or DR, it doesn't matter. You should always select your technique based on what you're x-raying and what size it is and what you're looking for. The quality of the digital image depends on many of the same factors as film screen, but what's different is that the digital image can be corrected. And so when we correct for it, when it's too low, you may get quantum noise. So here's an example from your book. This is a hip, well, it's actually the neck of the femur, but this is correct, and this was underexposed, but your equipment made it look okay. But look at all that noise right there. And even though it can actually adjust for low and high exposure, so you can have an overexposure. Now, you're not going to get noise on your image, but you're still overexposing your patient. The radiographer is still responsible for selecting exposure techniques that produce acceptable image quality while you also maintain a LARA. Exposures too low will adversely affect the quantum noise on the image, and exposures too high is excessive radiation exposure to the patient. It's recommended that radiographers continue to select the correct technique to produce diagnostic quality radiographic images regardless of the system that you're using. An important difference between film screen and digital is that digital image does not have the same visual cues as film does. When you have film, excessive or insufficient exposure presents an image with excessive or insufficient density. But a digital film can display with appropriate brightness whether you under or overexposed your patient within reason. So regardless of the receptor type, you, the radiographer, must select the required exposure factors of mass and KVP, and you should accurately position the patient for a variety of procedures because that's just as important as using the right factors. Your next quarter, you get to go into radiographic positioning and anatomy 1, and you're going to start learning how to do that. There are also various accessory devices, such as grids and collimators, and we still use those in digital imaging. So no matter what you're using, make sure that you know everything that we've already talked about up until this point. You know what mass to use, you know what KVP to use, you know when you use a grid or you don't use a grid. You always collimate as much as possible, and you don't expose the patient to any more than they should get. All right, so even though you're working with film or you're working with digital, it doesn't matter. You get remnant radiation that hits your image receptor and it creates an image. You want that image to be quality the first time. We have covered all of these things. I'm not going over them again, but there's some more. And we did not cover any of the film characteristics, except every now and then I'd mention that it's required in both systems equally. Now, I'm going to leave you with this x-ray of a sea turtle. And just so you know, that's kind of cool to me because I love turtles, have ever since I was a little kid. And I just think they're fascinating. This is an actual radiograph from a veterinarian service on the coast. And I want you to think about it. Even on this turtle, they use the appropriate technique to go through every bit of him. And what's unique about him that we don't have, they have a shell, they also have bones, they have all of these other things, but I can see everything that needs to be seen. And as a digital image, the good news is we could change this out here if we wanted to look at all the little, I don't know, do you call those toes? And then if we want to see the tail, we want to see the head. Make sure that you're using what you're supposed to be using. Take into account all of the factors that we've learned up until this point so that you understand what's going on. Okay, thanks guys. I appreciate it.